So yeah, in today's lesson, we want to cover the following objectives: eigenvalues and eigenvectors, some theorems that are associated with some eigenvalues, and then classification of linear systems, and then solving diagonalizable systems. So that's what we'll try to cover at this point in time. So let's just get to it without wasting much time. So first thing, so we're not going to spend much time on theory. We'll just lay some results, I expect you to know by now, then yeah, we'll move on to other things. So the first thing that we want to look at is the definition of eigenvectors and eigenvalues. You see, so what are eigenvectors? What are eigenvalues? That's the first thing that we want to understand. You see, suppose we have a vector space V in which an operation or an operational matrix A has been defined. You see, so suppose we have a vector space V in which an operational matrix A has been defined on it. So there is one way of introducing the language of eigenvectors or eigenvalues. So many people do it differently. So me, I'm going to use another different approach, but still the same definition. So one thing that you have to be aware of is that matrices, as far as their object, they are also vectors when you bring them inside the vector spaces, you see, because they have this ability that they can take you from one object inside a vector space into another object in that same vector space. So because of that they have all these properties, they can also be taken as operations whenever they are inside a vector space, you see. So now we are considering a vector space V in which we have this operational matrix defined on it. So suppose if for some V, an element of V, we have that. So if for some element V which belongs to V, we have that AV is equal to lambda V, then V is called the eigenvector corresponding to A, and lambda is called the eigenvalue. You see, like that. So this is one way of defining what an eigenvector is and what an eigenvalue is, you see. So when you take a matrix and introduce it inside a vector space, there are some objects which are such that when they're operated on by a matrix, they do not completely change to form new things. Yes, they do form new things, but they do not affect, change the vector in a more significant way. Because remember, what is it that makes up a vector if we bring it into the language of physics? You see. So remember, a vector, if you have a vector V there, one thing that characterizes a vector, there is what we call magnitude, and then there's what we call direction. you see. So these are the two things that characterize this object that we call a vector when we bring it into the language of physics. So if they exist a vector which is such that when an operator operates on it, that vector only deforms or changes its size, but its direction remains the same, then we call that vector an eigenvector associated with matrix A, you see. So the scale by which it changes its size is what we refer to as an eigenvalue. So is that clear enough?
Yes, yes, it is.
You see. So this is how we can define this. So that's it when it comes to the definition of eigenvectors and eigenvalues. So it's just any vector which obeys this property is said to be an eigenvector corresponding to whatever matrix is involved. And the scaling factor is what we refer to as the eigenvalue. So when it comes to then to this definition, one of the things that follows immediately is that you are introduced into how one can actually obtain these eigenvectors and eigenvalues that correspond to whatever given matrix is, the given square matrix is there, you see. So in this session, we are not going to try and follow through that whole process of learning how to find eigenvalues and eigenvectors, because I believe it's something that by now you must be fine with that. So do you have any challenges when it comes to finding eigenvalues and corresponding eigenvectors?
I don't have many problems, but like maybe one or two questions. I'll just make like a small calculation error here and there. Otherwise, generally it's okay. But sometimes like the really harder ones, I think there was one tutorial that was really hard, and then I think my tutors had to help us with that one. But otherwise, most of it is okay.
So what I'm going to do, I'm going to actually look at an example, but this example is not actually to show you how to find eigenvectors and eigenvalues, but I want to actually use this example to introduce some concepts that might be helpful on what you are going to see later as we go through this. So what we're going to do is, let's look at this example, which says determine the eigenvalues and the corresponding eigenvectors of the matrix So the matrix is 0, 0, -2, 1, 2, 1, and then 103, like this. So this is a matrix that we have, and we are asked to find the eigenvalues and the corresponding eigenvectors of this matrix. So I'm not doing this to show you, but I want to introduce some certain concept or certain terminology that is associated with this whole algebra. So let's get to it. So let's give our matrix a name. So we'll refer to this matrix and call it A. So we'll say let A be our matrix, which is 0, 0, -2, then 1, 2, 1, and 103. So what we're then going to do is we're going to recall, you see, how do we actually find eigenvalues? You see, we know eigenvalues are given by what? How do you find? We know that eigenvalues, they are always found by evaluating the determinant of A minus lambda I and equal to 0. So if we create an equation using this ansatz, then we can get what we call a characteristic equation for that given matrix, and then we can find the value of lambda there, you see. So now what happens? So now what is the determinant of that? So the determinant of this matrix A is something that you write as minus lambda 0, negative 2, then 1, 2 minus lambda 1, then 1, 0, 3 minus lambda equal to 0. So this is the equation, or what we refer to as the characteristic equation. So now we know that this thing, since it represents a determinant, we know how we evaluate it. It's going to be negative lambda times 2 minus lambda 1, 0, 3 minus lambda. Then the 0 term will vanish, so we have negative 2, then 1, 2 minus lambda, then 1, 0 equal to 0. So what now? So we have negative lambda, and then we have the product of that separating that. So we have 2 negative lambda, 3 negative lambda, negative 2. Then we have this, which is 2 negative lambda equal to 0. So 2 negative lambda seem to be common. We pull it out. What remains? We have lambda squared minus 3 lambda, then minus 2 equal to 0. So we have 2 minus lambda. Then what we get here with lambda. So we need factors of negative 2, which give us negative 3. So it's what? Do there exist any factors of this, or I messed up here?
I have a question. See the 2 minus lambda times the 2 minus lambda in your third line from the bottom. Shouldn't it be positive?
Where?
See where you have so, comma.
Okay, so I see. So I factored this. Then what I did,
The next one.
I took this inside here. So I said negative and negative, I get that. Then I said negative and that I got negative. Then I have negative 2 that.
No, what I'm saying is, see when you wrote out the minus 2 into 2 minus lambda, wouldn't that be a negative value? So then when you multiply it by the minus 2 becomes positive. Because when you take the determinant, it will be 1 times 0.
You're saying here, or?
Yes. When you multiply it into.
Okay, see. This was this has to be a negative, so this has to be a positive term.
Yeah.
Excellent. Yeah, that's where the mistake is. So like that. Yeah, thanks very much for that. You see. So it means now our factors are simple: negative 1, negative 2. So we'll have negative 1, negative 2. So therefore, what happens here is that here we'll get 2, and here we'll get 1, and here we'll get 2 again. So these are our eigen values. So this is how we find the eigenvalues, like that, you see. So this is something that has to be very easy. And yeah, make sure you don't do the mistake that I did there, because yeah, it's a very dangerous one. So now, if we have our eigenvalues, we know that how exactly we can go about finding the eigenvectors. So for eigenvectors, we know that AV is equals to lambda V. You see. So we know that if as a vector V is some eigenvector, it has to satisfy this condition. So what I'm going to do, since we're working with the 3x3 matrix, we are going to say, let V be a matrix which checks the form alpha, beta, gamma, like that. So this implies now, if I want to find what these alpha, beta, gamma, and I have to substitute them into that expression that we have. So we have alpha, beta, gamma, then we have 0, 0, negative 2, 1, 2, 1, then 103. So now let's multiply this out and see what we get. So when we multiply this out, we can take, or maybe this row or whatever row is up to us. So the first one that I'll decide to take is to multiply the first row first and see what I get. So here I'll get negative 2 gamma is equals to gamma alpha, like that. Then what else? What else? And also there's something that's coming. I can multiply with this. I'll get alpha plus 2 beta plus gamma equal to, so I multiply from second row, so I'll get lambda beta. So I have my nice 2 equation here, which I'm going to solve for all the different values of lambda that we have. You see, so we have 2 values of lambda. Lambda is equals to 1 and lambda is equals to 2. So now let's illustrate the things that I wanted to actually talk about in this example. You see, so the first thing that I wanted to talk about is the concept of algebraic multiplicity. You see, so if you check here, one can make a conclusion that here in this problem we have 2 eigenvalues. We have lambda 1 equal to 1, and also we have lambda 2 equal to 2, but this seems to have repeated 2 times, you see. So whenever we have an eigenvalue like this one, whereby it appears as a root of the characteristic equation more than 2 times, then we refer to this as the multiplicity or the algebraic multiplicity of this eigenvalue, you see. So which means if something like this happens, we can actually write and say lambda 2 has algebraic multiplicity of 2. You see, so the goal of this example was actually to introduce you to some certain terms that we deal it in under this subject of eigenvalue and eigenvectors. So we have these 2 things which we refer to as the algebraic multiplicity and the geometric multiplicity. So the algebraic multiplicity is the number that tells us how many times a specific eigenvalue was obtained as a root of the characteristic equation, you see, or how many times that eigenvalue repeated as the root of the characteristic equation. So since here this one repeated 2 times, we say it has an algebraic multiplicity of 2, like that. So is that clear?
Yes, it is. For like the test stuff, do we have to write it there?
What?
That it's algebraic multiplicity, or can we just leave it as 2?
Yes, it's just 2 for now.
Okay, so we don't have to like write it, it's algebraic multiplicity. We just have to know it.
Yeah, we just have to know it. You see, it's just that it's an important thing knowing it, like yes, knowing these kind of things, like, because it helps a lot when it comes to the solution of systems, especially you as someone who is doing 2DE, you know that in differential equation, you come across whereby you have to learn how to solve both these 2 systems, the diagonalizable system and the non-diagonalizable systems. So if you understand this language, it becomes so much simple to solve all those different types of systems, you see.
Okay, yeah. I just want to know, because I didn't know whether that would be a mark, like, you know, when you're writing out the solution.
Yeah. I know now, you know, mark for this. It's just good to know.
Okay.
Then we say it also there is what we call a geometric multiplicity. We are going to see what that is as we go on and solve this problem. So let's proceed now with where we are. So now we have created equations which we like to solve now for different cases. So what we are going to do now, we're going to consider all those 2 different cases. So now we'll say for lambda equal to 1. So if lambda is equal to 1, what is going to happen? We see that we get something nice here. We see that we get negative 2 gamma is equal to alpha. So which means already I know what alpha is. So I'll keep my alpha to be that. You see, so that's it. So I'll call it my connection 4. So I know that this is it. And what else? So, and also I can go on and substitute my material. So I know that here I'll just get beta, which will go then become beta. So I'm left with a 0 there. So alpha, I know what alpha is. You see. So I know that alpha is equivalent to this term. So I can now replace alpha here and put this. So what does it mean? So this implies negative 2 gamma plus beta plus gamma is equals to 0. So what does it imply from here? So you see that these two terms are like terms, so they will give us negative gamma. So it means beta and gamma, 1 and the same thing. You see. So now, yes, what follows here? So do you see now that I can write my B as follows? So my vector V, which I know was alpha, beta, gamma, can be equal to alpha, which is negative 2 gamma, and beta, which is gamma, and gamma, which is gamma. So I can factor out the gamma, and what remains? Negative 2, 1, 1. You see. So yes, what do we see here? Do you see that this eigenvalue, first let's understand what we're trying to do here. Do you see that what we're trying to do in this whole process was to find a single eigenvector which corresponds to the value of lambda or the eigenvalue that we had. But now what we get is not just something which is single, because remember this gamma is something which is arbitrary because it was not specified or given a specific value. So it can take up anything. Do you see that?
Yes, yes.
So, which means we do agree that what we have here is actually a set of vectors, not just vectors.
Yes, so then it has the same direction, but the magnitude will change based on gamma.
Yes, you see. So first, what I'm trying to say, I want you to understand that what we have here is a set of vectors. All of them, they are multiples of gamma. That's one thing that we see. You see. So this set is a name. You see. So this set that we have here is called an eigenspace of 1 or of lambda 1. You see. So what you have here now, this whole thing, we refer to it as the eigenspace of 1. You see, and this one forms the basis of that space. You see, so you see this bracketed term, the negative 2, 1, 1, since it's going to be the one that creates all elements in the set, it becomes the basis. Is that
so clear? I just want to ask, so the eigenspace of 1, how would you say it's 1, for example, not eigenspace of 2 or?
Okay, the reason why I'm saying this is the eigenspace of 1 is because lambda was taken to be 1.
Oh, okay, all right.
You see,
so if it was 2, it'd be different.
So it's an eigenspace of the lambda that you are dealing with.
Oh, okay, all right.
So okay. That's it. And do you see that we have only one basis for this lambda? Do you see that for this lambda, we have only one basis, which is just this only?
Yes, yes, I do.
So the cardinality, you do know what cardinality is?
Yes.
Yeah, so the cardinality, remember, it is the number of objects that we have in a given set. So the cardinality of the basis of the eigenspace is what we define as the geometric multiplicity. Do you get that?
Why is the geometric multiplicity? Oh, is it because you can multiply it if lambda was something else and you would get another number by that factor?
No. So the geometric multiplicity is a number which tells us how many of the vectors form the basis of the eigenspace. So since we have one vector which forms the basis of the eigenspace, we say lambda corresponds to an geometric multiplicity of 1.
Okay, all right. Yes.
So that's what we mean by geometric multiplicity. So we can write it here. Oh, sorry, it's supposed to be geometric. You see, so that's what it is. So it's more like the cardinality of the basis set. That's what it is. You see. So now let's continue now and solve the next for 2 now. You see, so let's solve the problem when now we have 2. So for lambda is equal to 2, what is it that does happen there? See. So if lambda is equal to 2, let's see what changes we'll have. So here, do you see that we'll put 2? So the 2's will cancel. So we'll have negative gamma is equal to alpha. So we'll have negative gamma is equal to alpha. And also we'll have what? So let's put 2 also in the other equation. So ways here we get 2. So do you see that when we put 2, these will cancel? Do you see?
Yes. Yes. Yes.
So this will cancel. So do you see that you still remain with the same result that alpha is equal to negative gamma again?
Yes.
So this is what we only have. So what does this mean? So it means beta becomes a free variable. So when something like this happens, we say beta is a free variable. So meaning beta can take anything, but those, they have to satisfy that property. So what does that mean then? So this implies that now if I'm to write my V will be as follows. So instead of writing alpha, I'll replace it with negative gamma. Beta will stay as beta, and gamma will be gamma, because gamma is gamma again. So now, what do you see? Do you see that this now can be split into 2 subsets, one where there is gamma only, and one where there is beta only? So this can be written as gamma, -1 or 1 plus beta 0, 1, 0. So what do you see now? So this is, again, the eigen space of lambda 2 equal to 2. So what do you see now? Do you see that now we have 2 elements in the basis set?
Yes.
So what can you conclude from this?
Does it have 2 geometric multiplicities?
Yes, so therefore lambda 2 is a geometric multiplicity of 2. Nice. So that's what it means most of the time, that when we talk about these terms, this is what they describe. They tell you about the cardinality of the basis of the eigenspace. And the eigenspace is the set of all different eigenvectors which correspond to that typical lambda that you have been considering, you see. So which means now if you're asked, what is the eigenvector? You can choose any one of these. Because most of the time when we ask about an eigenvector, there are many different possibilities. You can choose them arbitrarily by taking lambda, gamma, and beta to be anything, but you can just take beta to be 0 and collect the other one, where you take that case to be lambda is gamma is equals to 1 and all that, you see. So 1 is fine to cater for everything, you see.
Okay. And like it doesn't matter which one you choose, like
Yes.
the model set either one.
Yes, as long you use this to choose, like you don't have to, okay. You have to make sure that there is a way of constructing whatever you've chosen by choosing suitable values of the gamma and the beta.
Okay. What would the suitable values be? Like
anything.
The base values like 1 or 0.
Like I can make this to be 0. If I make this 0,
yes.
This vanishes, and then I take this 1. If this becomes 1,
okay.
then my eigenvector becomes 0, 1, 0. That's it.
All right. Okay.
So like that. So that's it. So that's what I wanted to just display by this problem. Not to just do it for the sake of seeing, but to introduce these type of things so that you get to know them. So I think now we're cool with that. Now let's move on to the next thing. So there are some useful theorems that I think at times they can be kind of useful in problem solving. So there are just 2 theorems that I want to introduce. So there is the first one, Theorem 1. So Theorem 1, it says that if lambda 1, lambda 2, to lambda k are eigenvalues of the matrix A, then sigma lambda I, all I is equal to sigma AII, all I, like that. You see, so this is a very good theorem because it's actually telling us that if you have eigenvalues of a matrix, you can actually you can use them to find the trace of the matrix. You see that? Because it's telling us that the sum of the eigenvalues is equal to the sum of the diagonal element. So, which means trace of A, like that. So the sum of eigenvalues can be used to calculate the trace of a matrix. You see? So it's quite a cool result, though we don't need it for the trace because the trace is simple in all directions. You can either use diagonal elements or use eigenvalues. You see? Then Theorem 2. So if lambda 1, lambda 2, ... lambda k eigenvalues of matrix A, then get A. So if you have the eigenvalues of a matrix, when you have a matrix and you know its eigenvalues, you can use that to calculate the determinant. So the product of all eigenvalues actually gives you the determinant of a matrix. You see, so something immediately follows from this. What is it that can follow from this? If one of the lambda i's is 0, then what?
All would be 0.
Singular.
See, okay.
See. So if one of these becomes 0, then it means the determinant will become 0, and therefore the matrix A becomes a singular.
All right.
So this is a beautiful result that you have to know in linear algebra when it comes to the eigenvalues. So they are beautiful because they can provide all such information. You see. Then now, classification of systems. Or let me just matrices for now. You see, so we want to talk about, there are many ways of classifying matrices so far that one can come to study as far as linear algebra is concerned. But we want to just raise up an important classification of matrices, which is something closely related to solution of linear system of differential equations. So we want to introduce. So matrices can be classified as either diagonalizable or non-diagonalizable matrices. You see, so matrices can be classified using many different ways, but we have also another important classification, which is the one which classifies matrices as either diagonalizable and non-diagonalizable matrices. But what do we mean by that? What do we mean by that? What do we mean when we say matrix is diagonalizable? See. So formally, a matrix A is said to be diagonalizable if they exist an invertible matrix P and a diagonal matrix D such that A is equal to P D P minus 1. You see. So that's the definition that we have. That this is the formal definition that we have most of the time when we start talking about the idea of diagonalizable matrices. So if they exist an invertible matrix, so all these are square matrices anyway. So if they exist an invertible matrix P and a diagonal matrix D such that this statement holds true, then we say A is a diagonalizable matrix, like that. So this formal definition actually of it, though it's written informally, but that's the formal definition of diagonalizability. But it's actually hard to classify matrices if this is the only idea that you have about diagonalizable. You see, because how can you go about the process of finding these P's and D's? So we have other ways of actually checking out if a matrix is diagonalizable or it's not diagonalizable. You see, so how can we find if a matrix is a diagonalizable one or it's not diagonalizable without the use of this definition? So one way is by making use of one of these results. You see, if A is diagonalizable, one of these results must hold true. You see, so if A is a diagonalizable, a matrix, then one of these results must hold true. So let's just say A is an A by N matrix again. 1. A must have N distinct eigenvalues. You see, so if a matrix A, which is an N by N square matrix, has N distinct eigenvalues, this is a straightforward diagonalizable system. You see. Or 2, suppose then we do not have, but some things repeat there. Then what else must be true? You see. So if instead A has K eigenvalues with K less than or equal to N, then it must be the case that the sum of IL, I'm writing the, so I'm about to introduce something that you won't get, so you can't use this when you're writing exams. You see, so what does this mean? What does this mean? So what these things means, it just simply means geometric multiplicity of lambda I.
Oh, so like the previous example.
Yes.
Okay.
So this thing stands for the geometric multiplicity of lambda I. So what this result is telling us is that there are 2 different ways of checking if a system is diagonalizable or not. One way is to check if there are N distinct eigenvalues. So meaning there should be no eigenvalues which repeat. But it says again, suppose, yes, we do have some eigenvalues that repeat. How can we then confirm if it's still diagonalizable? So if it's still diagonalizable, then this must hold true. It means if you are to sum up the geometric multiplicity of all your eigenvalues, they must give you the total number of rows or the number of columns of your matrix. Is that clear?
Yes, it is. Okay.
Like, let's go back to the top example, to the one that we used here in the previous case. Let's see. Do you see that this system that we're dealing with, it gave us two eigenvalues?
Yes.
And it was a 3 by 3. Suppose you asked now to check if this is diagonalizable or not. Do you see that this system is diagonalizable? Why? Come, let's check. Do you see that we found that this lambda 1 yet an algebraic multiplicity of 1 here?
Yes.
And we found that this lambda 2 yet an algebraic multiplicity of 2 here. So do you see that the total multiplicity adds up to the number of rows of the matrix or the number of columns?
Okay, yeah, it makes sense now. Okay.
Yeah. So because when you say 2 plus 1, you get 3. So since the total algebraic multiplicity adds up to the number of columns, then we can conclude and say the system is diagonalizable.
Okay, so what you mean is like if ever they ask to prove it, this would be sufficient to prove it.
Yes.
Okay.
This will be sufficient.
All right. Okay.
This will be sufficient like that. But then my question now is, do you know how to diagonalize a matrix anyway?
No, I don't.
Okay. So suppose the problem says diagonalize the matrix minus 2, 2, 3, minus 2, 3, 2, and minus 4, 2, 5. Suppose you are given this matrix and you're asked to diagonalize this matrix. How do you go about diagonalizing a matrix? This is what we want to learn now. So the first thing that you can do, you can first give it a name. So you can call it a matrix A if you like. So let's copy it down, minus 2, 2, 3, minus 2, 3, 2, minus 4, 2, 5. So now what we're going to do from here is we are going to find the eigenvalues of this matrix. You see, so eigenvalues are given by what? So we know that if I want eigenvalues, I have to solve this determinant equation, minus 2 minus lambda, 2, 3, then minus 2, 3 minus lambda, 2, then minus 4, 2, 5 minus lambda equal to 0. So what follows from that? So what follows is that I can factor out negative 2, negative lambda, and then we know the whole story. So here I have 3 minus lambda, 2, 2, 5 minus lambda, then negative 2, then I have negative 2, 2, negative 4, 5 minus lambda, then plus 3, all that equal to 0. So I have negative 2, 3 minus lambda, negative 4, 2. So let's simplify. This implies what? So we can keep that as negative 2, negative lambda. And what do we get on the inside? So we have the product of these two together. So let's put it like that, 3 minus lambda, 5 minus lambda, minus 4, then with negative 2, then this multiplies that. So if this multiplies that, we see that we'll get 2 lambda, and then minus 10. So we'll get minus 10, but there is this one part where we'll get positive 8. So we'll get plus 2 again. I think I'm correct there if I'm not mistaken. Then plus 3. So here we see there is a subtraction that is going to come. So how can we handle it? So we know that this is going to be a negative 4. Then this is going to be positive anyway, multiplying that. So we get plus 12 minus 4 lambda, all that equal to 0. So this is a very ugly problem. But let's try and solve it and see where it all goes. So it's a very ugly one. So we have negative 2 plus lambda. Then here what we get lambda squared. Then minus 5 lambda minus 8 lambda. Then 15, so plus 11. Then we have negative 4 to lambda plus 1 plus 3. Then we have 8 minus 4 and equals to. So it's boring one because it didn't actually give us a thing that we can pull out and factor out, because even if we pull something out, so it means it has to be solved using the long process. So we have to now multiply everything inside here by these 2. So what do we get now? So we'll get negative lambda cubed. Or should I do that? Or should I first keep out the negative outside? So I take that here, I get lambda cubed. Then I get that negative 8 lambda squared plus 2 lambda, so it's 6 lambda squared. Then I have 11 lambda minus 16 lambda. So what is 11 minus 16 is minus 5. Then plus 22. Then minus what? So this side we have negative 12, negative 4, so we have negative 16 lambda. Then we have 24 minus 4. So 24 minus 4 is plus 20, equals to 0. So what happens? So I can divide everything by this negative so that my terms here are positive. I'll get lambda cubed plus 6 lambda squared. This will become positive. So I'll have 16 minus 5, which is plus 11 lambda. Then
wouldn't it be minus a lambda?
Is what?
Wouldn't it be minus 11 lambda?
No, what I did is I divided by this negative throughout. So these terms were not affected. These are the ones that became negative. So this is going to be a positive.
Oh, okay.
And that we get that. Then here we have a positive 2 minus that. So it's plus 2 is equals to 0. So this is more like a cubic polynomial where we now have to use our, what we call this, our factor theorem and stuff. But since so far there is no short way, I'll just end it here. I think now from here, if you just say let f lambda be equal to lambda cubed plus 6 lambda squared plus 11 lambda plus 2, you can take this as a polynomial and you use your factor theorem to get. But anyway, what was the question that I wanted? The question was how to diagonalize it, you see. So now we are here. So from here, we will get 3 eigenvalues. And it can happen that, okay, they do have maybe one of these two may be repeating or whatever, but we are going to consider a case whereby none of these are repeating, you see. So if now you want to find a diagonalizable version of matrix A, which we call D, then D is simply given by lambda 1, lambda 2, lambda 3, and everywhere else being 0. You see, so this is how you diagonalize a matrix. It's all about finding the eigenvalues, and once you have them, you just arrange them that way. In that way, along the main diagonal of the matrix, whereby all the other entries have to be 0. So this is what we call the diagonal form of matrix A. Then, if you want to find the corresponding P, then P is simple, you see. So P, the matrix P that we saw that we need most of the time for diagonalization process, is simply given by this. Each column of P is just the eigenvalue of lambda 1, eigenvalue of lambda 2, and the eigenvalue of lambda 3. Like that. So when you have eigenvectors of lambda, sorry, it's supposed to be eigenvectors, not eigenvalues. So let me write down. So here, AI, lambda I means eigenvalue, eigenvector of lambda I. So that's what it means. So when you get all your eigenvectors, you just arrange them in columns. They form what we call the matrix P, like that. So do you get that?
Yes, yes. Also, just for notation's sake, when we do write it out, do we have to write those lines at the top and the bottom?
No, you don't have. It's just that why I'm doing this, we do not have the eigenvectors themselves. So what I'm showing you is that, remember, an eigenvector will come out as some sort of a vector, like for example, e.g., you will get maybe V1 being -2, 4, 2. So what I mean by these lines is that this thing, you will put it there as a column. So it will be -2, 4, 2. Then the second one also will become a column, and the third will become a column.
Oh, okay. All right. I understand that. Okay.
So that's what it means there. So that's it. That's it. So now let's then look also at another powerful use of a diagonalizable form of a matrix. Why is this diagonalizable form so important to us? You see, so why is this very important to us? So let's understand. So well, the first reason is that it makes calculation of exponents easy. You see, it makes the calculation of exponents easy. But in what way does it make it easy? Suppose, e.g., suppose you are asked to find AK. Suppose you are given want to find a to the power k, where k can be very huge at times. You see, remember, well, how do we define AK? AK means you have to multiply this matrix with itself k times. Like that. So you have to take this matrix and multiply it with itself k times. So if a matrix A that you're dealing with is a diagonalizable matrix, then this exponent becomes so easy to find. How? You see. So if A is diagonalizable, whereby there exists the invertible, whatever, such that this property is true. So how can one calculate AK? Do you see that now if you want AK in such a situation, it should become, AK will become simple. A, dot, A, K times, which can be written as PDP minus PDP minus PDP minus PDP minus and so on up until you get this K times. Now look at what happens. Remember, this is a product. Now we have a product of a matrix together with its inverse element. What do we know about the product between a matrix and its inverse?
Wouldn't it be I?
It will be I, the identity matrix. You see?
Yeah.
So which means I can remove it completely because the identity, remember, is the same as 1. So what will remain is just P and these D's now next to each other. You see, the only P that won't be get affected is the one at the far end and the one at the start. All the P's in between, they'll be canceling themselves, each other in that manner. So which means now I will have this P as D to K, P minus 1, because I'll be having these D's repeating themselves K times also. Do you see that these D will repeat themselves K times? Because there were K of these things that I lined next to each other.
Yes.
So what do you see now? So do you see that now, if I want to find the power of a matrix, now I just have to find the power of a diagonal matrix.
I have a question. The P at the end and the start, wouldn't that also cancel out?
Yeah, but now the K doesn't have to do with them. The K part only affects this region, which means if this is your D, if your D is just 3 minus 1, 2, then 0, 0, 0, 0, 0, 0. And then if I want you to say find D20 now, what will be D20? D20 will be just 3 to 20, 0, 0, 0, negative 1 to 20, 0, 0, 0, 2 to 20. So what I will do then, I will then now take my D, K, and place it there and multiply it throughout. But the fact that now the exponent has been dealt with simple with dk, it has made the evaluation of all these things to be very much simple as well.
Okay. All right. Yes.
So that's how it works. That's how it all works. So
sorry. So the dk is only that diagonal element. So it'll just be 3, whatever it would be in the main 3 minus 1 and 2. I think for the zeros.
Yes.
Okay. All right.
So that's how it works. So this actually shows that it is very much useful a concept if you know diagonalizability, because if someone was to give you this as a task, it can be simplified, because suppose K is 20. Remember, if you are to do this product, 20 of them, how much it will take. But if you know diagonalizability, now it becomes a simple, you apply the power only on the diagonal portion, and then you evaluate everything out. You see.
Okay.
So are there any questions that we have now concerning all this?
No, it's clear. Yeah.
So yeah, since our time has run for us, so I think today we'll end it here so that you also get to assimilate and practice all that we showed here. I'll give you a question that will make you practice all the concepts that we did here. And then, yeah, we'll see more about this later.